In the previous lecture, we saw the power of augmenting paths. If we have a matching and an augmenting path with respect to that matching, then we can improve the matching. Also, we saw that if we have a matching and we can't find an augmenting path, then we know that we have an optimal matching, a maximum cardinality matching. In this lecture, we're going to go through the work of actually finding these augmenting paths. In particular, we're going to find augmenting paths in bipartite graphs. As a result, we're going to be able to solve the maximum matching problem in bipartite graphs. A bipartite graph is a graph where we can divide the nodes into two sets, V1 and V2. Any edge in our set of edges E is only going to have endpoints in V1 and V2. There's not going to be any edge that has both of its endpoints in V1 or both of its endpoints in V2. Here we have an example of a bipartite graph. And in general, the way we visualize it is as having the set of nodes V1 on one side, the set of nodes V2 on the other side, and the edges going between them. Intuitively, the reason that finding augmenting paths in bipartite graphs is easy is that we can assume that an augmenting path is going to start on either one side or the other of our bipartite graph. In this case, we're going to assume that it's going to start in the set of nodes V1. And end in the set of nodes V2. This is just symmetric, though. We could have assumed the opposite. In this example, we can see that this is the case. Our maximum matching here is in blue, M, and our augmenting path here is in fuchsia, or pink. We see that the augmenting path starts at a node in V1 and travels through our graph until it ends on a node in V2. This would be true for any augmenting path inside of this graph with respect to this matching. We're going to focus in particular on starting an augmenting path at exposed nodes in V1. Recall that an exposed node is any node of our graph that doesn't touch a matching edge. In this case, we have two exposed nodes. We're going to exploit these properties and eventually develop an algorithm that's going to find an augmenting path for any matching in a bipartite graph, or it will conclude that there is no augmenting path. The algorithm we're going to develop to find augmenting paths is going to be called the label scan algorithm. This algorithm is going to progressively label nodes and then scan the nodes after it labels them. It's going to start by labeling all the exposed nodes in V1 with a special label star. Then, it's going to look at all the currently unscanned, labeled nodes and choose one of them. What the algorithm does from here depends on the properties of this particular unscanned labeled node that we're about to scan. If our currently scanned node is a node I in the node set V1, then we look at every edge that's not in the matching and look at the other endpoint of this edge, say J, and label all of these nodes with the label I. So now all of these nodes that are on the other end of these edges, these non-matching edges, are labeled with I. This is only true if J is unlabeled. If J already has a label, we do not remove its label or replace it. On the other hand, if our node I is in V2 and I is an exposed node, then we terminate our algorithm. We found an augmenting path. The way we develop this augmenting path is by looking at this particular node and looking at the labels in the reverse order. After we take this augmenting path, we augment our matching and reset all of our labels. In the final case, if our node I is in V2 and I is not an exposed node, then we look at all the edges in the matching that touch this node, and we label the node J on the other end of this edge with the label I. So now J is at the other end of a matching edge, and I gets the label J, or rather J gets the label I. If the algorithm ever ends so that all of the labeled nodes have been scanned without finding an augmenting path in this middle step, then we terminate the algorithm and conclude that the matching we have is an optimal matching. This is a great description of the algorithm. and it's rather thorough, but to really understand this algorithm, we need to go through an example. We're going to work through the example graph shown with the particular matching M. To start the label scan algorithm, we first scan all the exposed nodes in V1. That happens to be nodes 1 and 4. After we do this, we pick one of the currently labeled but unscanned nodes and scan it. In this case, we'll pick node 4. We scan it, we see that there's one non-matching edge adjacent to it, so we scan the other end of this edge, or rather we label the other end of this edge with the node 4. Now we pick a new unscanned labeled node. Node 4 isn't available because we've already scanned it, so instead we'll pick 7. We scan 7, we see that it's adjacent to a matching edge, and so we label the other end of this edge, the node 3, with the label 7. Now we look for another unscanned labeled node. We can't choose either node 4 or 7 because they've been scanned already, so we choose node 3. We again go through the process and we end up labeling the node 6 with the label 3. We go through it again, we'll pick node 6, and then we'll label node 2 with the label 6. We'll again scan nodes, we'll scan node 2, which results in us labeling node 5 with the label 2. Now we're going to go through the final step. Here we're going to scan all the nodes, and let's suppose that we pick node 2 to scan. Node 2 now is in V2, but it's not adjacent to any matching edge. That means that this is an exposed node. Because it's an exposed node, we finally go to the part of the algorithm where we conclude that there's an augmenting path. And now we find the augmenting path. To find the augmenting path, we look at the particular node and follow the edges back according to the labels. Node 5 is labeled with 2, so we take the edge 5, 2 in our augmenting path. At the node 2, 2 is labeled with 6, so we take the edge 2, 6 in our augmenting path. At 6, we take the edge 6, 3. And at 3, we take the edge 3, 4, or 3, 7. At node 7, we take the edge 7, 4. In this way, we build the augmenting path by working through the labels in reverse order. This is the purpose of the labeling. Now that we have an augmenting path and a matching, we can improve the matching. We'll write the improved matching on this other graph. And we develop this matching by taking the union of all the edges in the matching and augmenting path and not including any edge that's in both the augmenting path and the matching. In this case, that means that we're going to include the edge 5, 2 since it's in the augmenting path, but not the matching, the edge 6, 3 since it's in the augmenting path, but not the matching, and the edge 7, 4 since it's in the augmenting path and not the matching. Given this new graph and new matching, we start the label scan algorithm again. We change the matching and reset all the labels. We start by labeling the node 1 with star. This is the only node of V1 that's exposed. We scan node 1 since it's the only node to scan, and that results in labeling node 5 with the label 1. We scan node 5, which results in labeling 2 with the label 5. 2 now is adjacent to 2 edges that aren't in the matching. So we scan node 2, and this results in labeling node 6 with the label 2 and the node 7 with the label 2. We scan node 7, which results in labeling node 4 with the label 7. And we scan node 6, which results in labeling node 3 with the label 6. In this case, our algorithm terminated by labeling all the nodes without finding any exposed node in V2. Therefore, there is no augmenting path, and the matching M that we currently have is optimal. The label scan algorithm terminates. At the termination of the label scan algorithm, we can say quite a few things about the labels. We'll focus on both the labeled and unlabeled nodes. To go through these properties, we're going to work with an example that's different than the example we used to actually run the label scan algorithm. you may want to pause the video and verify that the labels shown are the labels that would be returned by the label scan algorithm, keeping in mind that the two green nodes are unlabeled. We're interested in proving three properties. The first is that the set of unlabeled nodes in V1 and the set of labeled nodes in V2 constitutes a cover of all of the edges in our bipartite graph. Second, at termination of the algorithm, this cover is actually equal to the size of our matching, and as a result, this matching that we have is optimal. Finally, the set of labeled nodes in V1 is going to be smaller than the set of labeled nodes in V2. We're going to prove these claims by making a series of observations. The first observation is that there is no edge that goes between a labeled node in V1 and an unlabeled node in V2. And we can break this claim into two pieces. If the edge is a non-matching edge, then if it touches a labeled node in V1, then the other end of this edge has to be labeled. That's how the label scan algorithm works. On the other hand, this edge could be a matching edge. If this is the case, we consider one of the labeled nodes in V1. In order to label this node, we either have to start at a labeled node in V2 and traverse a matching edge, or this node has to be adjacent to no matching edges. In either case, if we look at a labeled node, it has to be adjacent to either a matching edge whose other end is labeled, or adjacent to no matching edge. So for every matching edge, it can't go between a node that's labeled in V1 and a node that's not labeled in V2. Since there are no edges from V1 plus to V2 minus, every edge has to touch either V1 minus or V2 plus. So these set of nodes consist of a cover. As a result, this cover has size at least the size of the matching. That's because the cover is an upper bound on the size of any matching. We proved this in the previous lecture. Now we make two observations about matching edges. The first is if we have a matching edge and it touches a labeled node in V2, then the other end of this matching edge also has to be labeled. That is, this matching edge touches two nodes, both of which are labeled. On the other hand, if our matching edge touches an unlabeled node in V1, then the other end of this matching edge has to be unlabeled in V2. That is, this matching edge has to have both of its ends unlabeled. Because every matching edge either has both of its ends labeled or both of its ends unlabeled, if we look at all of the unlabeled nodes in V1 and labeled nodes in V2, every matching edge touches at least one of these vertices. So the size of our matching has to be at least the size of this set of vertices. Since we also know that this matching is at most the size of this set of vertices, we know that this matching is exactly the size of this set of vertices. That is, our matching exactly meets the size of our cover. Because our matching meets the size of our cover, and our cover is an upper bound on the size of a matching, we know that this matching has to be optimal. The final thing we have to show, which is actually a small error here, is that the set of labeled nodes in V1 is larger than the set of labeled nodes in V2. Although we could prove this formally, it really follows from a simple observation. If we ever label a node in V2, it has to emanate from some labeled node in V1. In this way, we can match every labeled node in V2 with some labeled node in V1, so we have to have more labeled nodes in V1. These are the properties we'd like to prove. The main one being that at the termination of the label scan algorithm, if we don't find an augmenting path, then the matching we have is optimal. That's because it meets the value of our upper bound, the value of our cover. And importantly, we've also found exactly what the cover is as well. So we've found our matching upper bound. In summary, the label scan algorithm is either going to find an augmenting path and produce a matching of higher quality, or it's going to terminate with no augmenting path, and when it does, we can prove that the matching that it has is optimal.